Now we have two unbiased dice that are rolled. Unbiased means they're fair, they're not tricked. So we consider the events. We have A, the numbers on the upper face are equal, and we have the event B, the numbers on the upper face are odd. Now we need to find the probability of each of the given four events. The first one, we need to find the probability of event A. Now, by definition, the probability of event A is equal to the total number of outcomes for event A divided by the total outcome of the sample space. So, first, we need to find the total possible outcomes, which is N of U. Now, over here, since we are rolling two dice, now each die has 6 faces. Therefore, it has 6 possible outcomes. Each outcome is from 1 to 6. So, basically over here then, the total number of possible outcomes N of U is 6 possibilities for the first die times 6 possibilities for the second die, which leaves me with 36 possible outcomes. So this is for N of U. Now we need to find the total possible outcomes for event A. Now event A is defined by the numbers on the upper face are equal. Now the faces are equal when we have the numbers showing 1 and 1, the numbers showing 2 and 2, or 3 and 3, etc., all the way to 6 and 6, following the same pattern. We must have equal faces on the upper sides. So that leaves us with 6 possible outcomes for A. Therefore, the probability of A is 6 out of 36, which simplifies into 1 out of 6. So the probability of event A is 1 out of 6. So we can represent that probability as a percentage by multiplying it by 100. 1 over 6 times 100 gives me the percentage of occurrence of event A, while 1 out of 6 gives me the probability of occurrence of event A. Now, if we move to event B, now event B is defined by the numbers on the upper face are odd. When the numbers on the upper face are odd, now for each die, we have 3 possible faces that are odd, which are 1, 3, and 5 for each die. So this is why, of course, for the probability of B, we need to divide by the total possible outcomes, N of U. Now, as for the total possible outcomes for event B, it's basically 3 for the first die multiplied by 3 possibilities for the second die, which leaves me with 9 out of 36, which simplifies into 1 out of 4. Therefore, the probability of event B is 1 out of 4. Now, for the probability of A inter B. Now, A inter B represents the intersection of events A and B. Now, the intersection of events A and B means that the numbers on the upper face are equal and odd at the same time, which leaves us with 3 possibilities, which are 1 and 1, 2 and 2, sorry, that should be 3 and 3, and 5 and 5. So 3 possible outcomes here, so the probability of A inter B is equal to 3 out of 36, which simplifies into 1 out of 12. Now, as for the probability of the union, now we have this property that states that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A inter B. So we already have the 3 probabilities calculated. So the probability of A is 1 out of 6 the probability of B is 1 out of 4, and the probability of their intersection is 1 out of 12, which by adding those three probabilities and simplifying our answers, we obtain a probability of 1/3. So we have a probability of 1/3 to obtain the number on the upper face is equal or odd. So basically, the union is an OR, and the intersection is an AND. So when we say A or B, which is the union of the two events, it could be A occurring or B occurring or A and B occurring at the same time. While we say A and B, which is the intersection of the two events, A and B must be occurring simultaneously in order to have their intersection. Now, if we move to this next example here, we have a fair coin that is tossed 3 times. By tossing a coin 3 times, in part A, we have to find the sample space. We're not just looking for the total possible outcomes here. We have to list them. We have to list all the possible outcomes. So over here for the first coin, when we toss the coin the first time, we have the possibility of obtaining a head or a tail. When we toss it again, if we had a head for the first toss, then we have the chance of having a head or a tail again for the second toss. Similarly here, we have the possibility of obtaining a head or a tail. Now when we toss it a third time, we have the possibility of obtaining a head or a tail for each of the previous possibilities, which leave us with 8 possible outcomes. Now don't forget that when we draw a tree diagram to find a certain probability, we read the outcomes vertically. So over here I have 3 heads. Then the second outcome is 2 heads and a tail, etc. So to answer part A, we need to find the sample space, which consists of those 8 outcomes we just found. So we have here U equal to the set containing 3 heads, 2 heads followed by a tail, a head followed by a tail, then by a head again, then a head followed by 2 tails, and a tail followed by 2 heads, a tail followed by a head, then by a tail again, 2 tails followed by a head, and 3 tails eventually. This is supposed to be a T, not an H. Sorry about that. Okay, now for part B. They're asking us to find the probability of obtaining exactly 1 tail. Now, set U, which is the set we found in part A, basically represents all the possible outcomes. So we need to see among those all possible outcomes, how many out of them include exactly 1 tail. Exactly 1 tail, so that's exactly 1 T, which we have. This is one of them here, this is the second one, and this is the third. So basically those are the only outcomes with exactly 1 tail. So if we call A the event of obtaining exactly 1 tail, then the probability of event A is 3 out of 8. So whenever you need to find the probability of a certain event, if this event was not named or defined in the given, you'd have to name it yourself before you use any letter as the name of the event. Now over here in this next example is an example that shows us how to use Venn diagrams in order to find probabilities. Now over here, if we read through this example, we have a group of 50 students. So basically we have our sample space here, which we're calling U, containing 50 students. So N of U is equal to 50. So we have 10 students that have blue eyes and blonde hair, while 12 have neither. So basically we have here two subsets of U, which one containing the students with blue eyes, and the second one containing the students with blonde hair. So over here we named BE as the students with blue eyes and BH to represent the students with blonde hair. Okay, now over here they said that we have 10 students that have blue eyes and blonde hair at the same time. At the same time, that's the intersection. The intersection which is the part in common. So here in the intersection, I have exactly 10 students. Now, over here, they said we have 12 students that have neither blue eyes nor blonde hair. So out of the two sets representing blue eyes and blonde hair, we have 12 students in the class. Now, if the total number of students with blonde hair is 34, now when they say the total number of students with blonde hair, over here they did not exclude the intersection, so that's including the intersection with the blue eyes. So over here, this is the set representing all the students with blonde hair, and we know that the total number of students with blonde hair is 34. Since 10 of them, we already have 10 of them placed, then we have 24 remaining here. Now, if we look at the Venn diagram before we continue, just to give a small interpretation of the numbers we have there. So in BH, we have 10 and 24, which represent the 34 students in the class that have blonde hair. Now, the 10 students here have blue eyes in addition to blonde hair, while the 24 students there have only blonde hair and don't have blue eyes. So finally, they're asking for the number of students with blue eyes. So the number of students with blue eyes basically is everything we have inside this domain here. So over here, I already have 10 of them placed. So all I need to do now in order to find the number of students with blue eyes is to determine how many students have blue eyes and not have blonde hair. So basically, if I call that number of students X, so we know that in total we have 50 students. So X plus 10 plus 24 plus 12 is equal to 50. Those represent all the students in the class. So basically, if we add those up, we have X plus 46 equal to 50, which leaves me with X equals to 4. So X being 4, it means that I have 4 students in the class that only have blue eyes and don't have blonde hair. So the total number of students with blue eyes, which is N of BE, is basically 4 plus 10. That's including the students in the intersection, which is 14. Now, of course, in this example, we did not really find any probabilities, but we can use such a reasoning with probabilities as well. Over here, we were only working with total number of elements inside each set, which in a similar process, we can work out examples in order to find probabilities. Similarly to this example here. Now they're saying at New Blue Bay International School, 15% of the diploma students take mathematics HL, and 20% of these students take physics HL. 21% of the students take physics HL, but not mathematics HL. Now, over here, they're not really giving you the number of students in the class. they're just giving you percentages. And we've seen that probability and percentages are basically equivalent. So when I say 15% of the students, that's equivalent to a probability of 15 over 100, which is 0.15. So basically, we can turn a probability to a percentage by multiplying it by 100, and we can turn a percentage into a probability by dividing it by 100. So over here, in order to find the probabilities that they want us to find, all we need to do is basically convert this given into a Venn diagram, similarly to what we did in the previous example. So over here, if we represent the whole class by the sample space U, we have the students that are taking Math HL, which we can call by MHL, and we have the students taking Physics HL. Now, the remaining students in set U, which are outside the domains of Math HL and Physics HL, are basically the students that are taking other courses. So over here, we have that 15% of the diploma students take Mathematics HL. So over here, 15% take Math HL, which 20% of them also take Physics HL. What I underlined in green here is basically the probability of the students that take Physics HL that are already taking Math HL. So over here, in order to find the students that are taking both Math and Physics HL, which is the intersection, so that's 20% of the 15% of students taking Math HL. So that's represented by 0.2 times 0.15, which is basically 0.03. So that's the intersection. So over here we have 0.03 in the intersection. Now, if we fill in the rest of the Venn diagram, so if we go back to what I underlined in blue there, they said 15% take Math HL, so that's a probability of 0.15. The probability of 0.15 is basically the probability of all the students taking Math HL, including those taking Physics simultaneously. So I already have 3% of them in the Venn diagram. So this number of students taking only Math HL and not Physics HL is 15% minus the 3% we have here. So we're left with a 12% or a probability of 0.12. Now, if we move on, we have 21% of the students taking Physics HL and not Math HL. So over here, the 3% in the intersection are not part of those 21%. So this is where we have 0.21 here. That's a probability of 0.21. So now in part B, what do they need us to find? They want to find the number of students that neither take Math HL nor Physics HL. So basically they're asking us to find the number of students outside both domains in the sample space U. Now over here in the previous example, if you go back to the previous example, the sample space had 50 students. So basically when I filled in the Venn diagram, I ended up adding all of them to 50. Now, if we're speaking percentages, if we distributed percentages among a certain class, then the total percentages should add up to 100%. So, as we've said before, if we want to go back from a percentage to probability, I divide by 100. So 100% divided by 100 is 1. So the total probability should add up to 1. So over here in part B, we have that 0.12 plus 0.03 plus 0.21 plus x should be equal to 1, which leaves me with x equal to 0.64. So the probability of having a student that is neither math or physics HL is 0.64 or 64%. If you look at this example here, which uses some counting techniques for finding probabilities. Now, we have 14 girls and 11 boys in a class. 2 students are selected to represent the class in the school assembly. In how many different ways can the 2 students be selected? So over here, in part A, we're looking for all the possible groups of 2 students that we can choose. So what we're looking for basically here is the total number of outcomes of the sample space. We're looking for n of u. So over here, we have 14 girls in the class and 11 boys. So in total, we have 25 students. So out of those 25 students, I need to choose 2. Now over here, we're choosing 2 under no restrictions. So basically, choosing student A before student B is the same as choosing student B before student A. So over here, the order of the choice does not really matter. So this is a combination of 2 out of 25. So for part A, n of u is basically the combination of 2 out of 25, which could also be denoted as 2 out of 25 vertically, which is equal to 300 using our calculators. Now in part B, we need to find the probability that the selected students are either both girls or both boys or of different gender. Now we've seen in part A that we have 300 possible groups of 2 to choose out of those 25 students. So basically, if we call this event A, this event B, and this event C, we already have the total number of possible outcomes from part A. So in order to find the probabilities of A, B, and C, all I need to do is find the total possible outcomes for events A, B, and C. So now in part B here, if the 2 students chosen are girls, then in that case the 2 students chosen are chosen from the 14 girls in the class. Of course, we're still working with no order here. So basically the probability of event A is the combination of 2 out of 14 divided by the 300 possible outcomes, which is 91 out of 300. So the probability of choosing a group of 2 girls is 91 out of 300. Now for part I, choosing a group of 2 boys. To choose a group of 2 boys, we've basically then chosen the 2 boys out of the 11 boys in the class. Therefore, the probability of B is the combination of 2 out of 11 divided by the total number of possible outcomes, which is 300, which simplifies into 11 out of 60. And finally, of different gender, a group of 2 students of different gender means that I've chosen 1 out of 14 girls and 1 out of 11 boys. Therefore, for part I, the probability of C is basically the combination of 1 out of 14 multiplied by the combination of 1 out of 11 divided by 300, which is the total number of possible outcomes, which simplifies into 77 out of 150. So the probability of choosing a group of one boy and a girl is 77 out of 150. Now finally, we exclude with experimental probability. Now what we've seen so far is how we calculate probabilities theoretically. Now probabilities could also be conducted by experiment. So over here, by conducting an experiment or collecting data, you find the probability of the event as the relative frequency of the event, which is the frequency of occurrence divided by the number of trials. For example, if we look at the table which shows the relative frequencies of the ages of students at a high school. Now the students aged 13 have a relative frequency of 0.15, which means that 0.15 is the probability of choosing a student with an age equal to 13. Similarly, we have a probability of 0.31 of choosing a student aged 14 years old, etc. So, now in part A, what we need to find is the probability that the student randomly selected is 15 years old. So, if we look here, the students aged 14 have a relative frequency of 0.21. Therefore, 0.21 is the probability of having the student selected being aged 15 years old. Now, the probability of having a student 16 years old or older. 16 years old or older, if we look here, 16 years old or older, basically 16 or 17 years of age. So the probability of this event is basically the sum of the probabilities of each, since over here having a student aged 16 or 17, that's the union of the two sets, and those are two events that are mutually exclusive or incompatible. They have no intersection because I cannot have a student aged 16 and 17 at the same time. So therefore, the probability is the sum of their probabilities. So over here, it's 0.19 plus 0.14, which is equal to 0.33. And finally, they're saying that in total we have 1,200 students in the school. We need to calculate the number of 15-year-old students. Now we know that the probability or the relative frequency of having a 15-year-old student is basically the frequency of occurrence, which is the number of students aged 15 years old divided by the total number of students in the class. And we know that this probability is basically 0.21. So 0.21 is x divided by 1,200, which leads me to x equal to 0.1 times 1,200. Then x is equal to 252. So eventually I have 252 students of 15 years of age.